Okay, all right. Good morning, everyone. I'm Hiren Prada. As you can see, my name is pronounced as Hiren Prada. Always, when I pronounce it, people always cannot make out the T if especially if I'm speaking to someone new on the phone. So I always say it's like Prada with a T and without the money, but it's pronounced exactly like that. So I'm assuming everyone has read my emails. If not, you are supposed to read your emails, announcement, especially your official Cal Poly emails, okay, from your professors. This is the only approved method that we are allowed to use. So if you went through my office hours page, there's a specific note in there which states why we only can communicate using your Cal Poly email IDs. Anyone? Two reasons why. Yes, that's true. And the second and more important reason, if your name was John Smith, I could create an account called john.smith@hotmail.com, which is still in existence, by the way. And I could request personal information about you from anybody, from any one of your professors. So if you're busy, we would not take a look at whether it's your official Cal Poly ID or not, and we would inadvertently disclose your personal information to somebody else. And so your Cal Poly email ID is officially verified. It's allotted to you, is assigned to you. So anytime you communicate with anybody in Cal Poly, always ensure that you use your Cal Poly email ID. Okay, that's one big important reason. Anyway, all right. So the holiday on Monday could not be helped. Holidays during the quarter is fine. I can squeeze, we can squeeze things faster or slower. But when it's right at the beginning of the quarter, which is unusual, it does complicate things a bit. And that's why the homework assignments are like bunched up at the beginning. But most of the early homework assignments are basically to refresh students' memories. So in the past, what I've noticed is students might have taken the physics classes maybe 2 quarters, maybe more than a year ago. And so then they have a hard time catching up with the material. So the analysis techniques that we will look at are based on the techniques that you've already learned. But if you are not proficient in those techniques, then everything is going to be a blur. Okay. There are several things I'd like to get through, but there's just not enough time. So I'm going to jump directly into the lecture. Syllabus, again, I sent a couple of emails out. Make sure to read through the syllabus. It's probably unlike anything you've ever seen before. There's a lot of information in there. It reads more like a legal agreement. And the reason is, again, it is a legal agreement. It's an agreement between the instructor and the student. This is what the student can expect of the instructor in the class. And of course, also the instructor outlines the expectations from the students, right? So basically it is an agreement. There are some rules that are outlined in there, and it just keeps building on and on because every quarter or every year, there will be some questions arising, and then inevitably it comes back to, you did not tell us this at the beginning of the quarter, so you cannot do anything about this. And so in an effort to alleviate that, we have to keep adding more and more stuff. If you have any needs, if you have any need for accommodation, please reach out to me as soon as possible so that we can make arrangements, whether in class or online. Attendance, as I mentioned and stated in the email, I do not mandate attendance. I do not take attendance. You are adults. I treat you as adults. You are in charge of your own education, right? You know better than me what you need. So if you wish to attend class in person, which is great, that's the best way to learn, great. If you wish to attend online, that's also fine. If you do not wish to attend online, if you just wish to watch the recorded video, that is also fine. If you do not want to do any of those three things, that is also fine. Okay, as long as you submit the work that is assigned to you and you keep up with the assigned work, that's all that matters, right? Doesn't really matter how you learn. The more important thing is that you learn. Okay. I'm very accessible. My office is in Building 20, which is right across the old antique looking building, which is probably one of the oldest buildings on campus. It's in the shape of an E. And as some of our older professors like to say, it's kind of the geographic center of the campus. It's room 117. It's a shared office space between me and 4 other faculty members. But again, I have an open door policy. So if I'm in my office and students want to come by, say hi, have a question, or just passing by and want to say hi, that's also fine. Okay. Anytime you want to come in, that's fine. My office hours page is online. So you can look at the schedule, see what works for you. There are fixed office times where I'm guaranteed to be in the office, but I'm also in the office outside of those times. So let me open that up. And share. I said I wanted to jump right in, but it'll take a few minutes to actually go over stuff. So the office hours page, page lists my schedule and the rooms that I'm available in. When I'm teaching a lab, I'm in the lab 9 hours a week. I'm in the same building. It's in room 126. If students want to come by and ask a question, that's absolutely fine. Okay. So if you have a question, if you want to get answered, you can stop by for a few minutes. I'd be happy to answer them. Of course, when I'm teaching a lab, my focus primarily is on the students who are doing the lab. So you may have to wait a little bit, but you will get your question answered. Okay. So office hours here, Wednesday and Friday, also during any of the lab times. Any of the olive green notations that you see here are also office availability. This is not fixed right now. I have lab meetings on Mondays. Depends on the schedule and depends on the students who show up, but I might change that going, as we progress into the quarter. So that's regarding the office hours. Class materials, slides are already available on the Canvas website. So if you have not yet taken a look at those, you can go ahead and do so. All of the slides and all the notes are already available. You can download those if you wish to annotate on your own. The other more important method is basically Microsoft's OneNote. Let's see if I open that up. Now, some students have signed up for the OneNote. If you have not yet done so, please go ahead and do so. OneNote is a very powerful software, especially for college students. It actually is like a digital version of a notebook. You can have multiple sections, multiple pages in each sections. You can have a separate notebook for each class that you're taking. And I use the class notebook feature of this one notebook. And what it does is, let's go to section 2. What it does is I can actually write on here. So it's a digital whiteboard, right? And if you have trouble reading my chicken scratch, just let me know. I can rewrite. Okay. Handwriting is a lost art. So anyway, this is the only content that is recorded, right? So my voice, whatever I speak is recorded, and the shared screen feature. This is also available online. So students who are online right now can actually view this. They can hear me speak. They can also see me via the camera that's here. But this is all recorded. Everything that takes place in the classroom is recorded, and it's placed online for students to review. Okay, so you have 3 ways to actually attend this class. You can attend in person, attend online, or you can watch the recorded lecture video. So the important thing about this is that when students sign up, Class Notebook automatically updates your end of the notebook, meaning anything that I write here will be available to students at their end in real time. Like a few seconds later, when your notebook syncs, you should be able to see this. So this alleviates students from taking notes, especially when we have to talk a lot and we move at a fast pace. Students might, get left behind just trying to note down everything that I'm saying, right? And so this alleviates students from actually taking down detailed notes. You can still take notes, obviously. Again, note taking is also an art form. You can actually mark the times, note the spaces where I've spoken about specific things. You can go back and review the lecture notes, but this is already available to you at your end. Anything that I write here, any annotations I make is available to you at your end. So I strongly urge you to actually sign up for the class notebook. You can do so using the Canvas link directly from inside Canvas, okay? One thing about that is that the My annotations and these pages are not editable at the student's end. That is just how they have designed it. Okay, I have no control over that. So you probably would not be able to write anything on these notes yourself. You can make a copy of this and write a note, but you would not be able to write directly on top of what I am writing. It's a one-way street. That's how Microsoft designed it. Yes. Yes. Yeah. So right now, the lecture video link is linked to the old playlist from winter 2024, just the previous quarter, just to show students how, how the videos would appear. It's a playlist link. You can subscribe. You can mark. It's not monetized, so I don't make any money off of it. But typically, I would go back to the office and I would update the videos and upload it shortly after lunch, right around lunch. So maybe like 1 or 2 o'clock. Sometimes it might take until the end of the day, but typically within 24 hours, the videos are posted online. Okay, so if there's a delay, if I get busy, we caught up doing things, just send me an email. Say, hey, Professor Tarada, Dr. Tarada, these videos are not posted yet. I'll go ahead and do so. Okay, so these are the 3 important things I wanted to note, right? I'll talk about the final exam on Friday. Okay, so let's move ahead. Pretty much closer to the end of the chapter. KCL and KVL. How do you pronounce this name? Kirchhoff. So when I'm from India originally, so the way we pronounce this name is Kirchhoff. And so I was in a meeting when I first, when I first arrived to Cal Poly, which is about 6-7 years ago. And somebody kept saying Kirchhoff. And I was like, I feel dumb. I don't know who that person is and what law are they talking about? And then it's like light bulb went off like 30 minutes into the meeting. That's when I realized they're talking about Kirchhoff. But apparently, he's a German physicist. The actual German pronunciation is Kirchhoff. None of us lived during his time, so we don't know if that was the actual pronunciation or not. But modern day German language, that's how it's pronounced. Anyway, so if you hear me say Kirchhoff, this is who I'm referring to. Okay, Kirchhoff's current law and Kirchhoff's voltage law, KCL and KVL. Basically, based on the law of conservation of energy, essentially it states that the sum of currents entering a node and the sum of currents leaving a node have to be equal, right? And so he came up with 2 laws, current law and voltage law, based on the law of conservation of energy. Sum of all the currents would be equal to 0. Sum of all the voltages around a loop would be equal to 0. So let's briefly look at what a node is first, what a loop is, and then we'll go into the law, right? So a node is basically any junction in a circuit where 2 or more components come together. Okay, it's any junction in a circuit where 2 or more components come together. So as you can see here, you have component B and you have component C. Let me use red. So this is a node. Okay. Also, if you follow the line, you have component A also connected. So here we have 2 and more, 3 components coming together. So anytime you have 2 components connected together, that's a node. So this is a node. This is a node, and this also is a node. So node, again, is simply a junction where 2 or more components are connected together. Online students, I will not be monitoring the chat window. So if you have a question, please speak up. The speakers in the classroom are on and the volume is sufficient. So if you have a question, again, just unmute yourself and speak up. Okay, so that's a node. Now, when you connect a component to any other component, you see these lines here. These lines represent wires in physical life, in real life, right? So basically, something like this, a cable that is running from the keyboard to the computer is a conducting wire, okay? This wire, again, it conducts electricity or allows a pathway for the electrons to flow through. Hence, it's called a conductor. Okay, conductor. Now, this is electric circuit theory. We are learning theoretical analysis. Everything in theoretical analysis is ideal. Okay, is ideal. We do not take any practical considerations into account. When I say ideal, it means that the conductor will have 0 ohm resistance. Will have 0 ohm resistance for any length of wire, whether it is a dot or a small dash, short line, or a really long line, they're all the same. Okay, they're all the same. So the point being that in the circuit diagram, we are drawing A as a very long line, and you see it like, turning towards the right. But in physical life, in real life, the wires do not have any, any sharp lines like that. You can see wires running all over the place here. There are cables here. All of these are conductors, right? They're just going from one point to another, making a connection. So this is a node. Can everybody see this? Right? This is a wire right here. This is a node because the signal at one end does manage to reach the other end. So in real life, there are some considerations we take, right? A real life wire has resistance, it has inductance, and it has capacitance. But the values of these resistances, inductances, and capacitances do not rise to the level of interference. You've seen those orange extension cables, right? Long orange extension cables. You plug it into a wall, which is, by the way, what is the voltage coming out of your power outlets? 120 volts. In North America, it's 120. It's 110 to 120 volts. It fluctuates, but we like to say it's 120. Outside of North America, many places in Europe, Asia, Japan, no, not Japan, Far East, India, it's all 220, 230, or 240 volts. It's kind of double. And there is a technical reason for that. We'll talk about that later. But this is a question that might appear on the final exam. Okay, not explicitly, but it would simply state you plug this into the power outlet. Well, then everybody should know what the voltage is for a power outlet. And it's not something that only an engineer should know, right? It's general knowledge. When you're plugging anything into a wall, you should know what voltage you're using. Every adapter that you plug into a wall has a specification, and that specification will list 100 volts or 200 volts, or 240 volts. Anyway, coming back to our point, you plug a power outlet, you plug a orange extension cable into a power outlet, 100 foot, 25 foot, doesn't really matter. At the end of that extension cable, you would still expect to obtain 120 volts, right? And so that entire 100-foot long cable is one single node. Okay, it's one single node. So a node is any junction in a circuit, conducts electricity. A wire conducts electricity, hence it's known as a conductor. And in ideal conditions, in theoretical conditions, we just assume that it has 0 ohm resistance. So when you have, I'm going to wipe this out right here. When you have electrons moving through a circuit, we say that the current is flowing. Current is nothing but the rate at which charge is transferred. Okay, is the rate of flow of charge. Charge is coulombs, right? And rate of flow of charge, meaning it's coulombs per second, which is one of the questions in one of the homework, by the way. Okay, so that's your answer. What is the definition of current? It's the rate of flow of charge. Electrons move through a circuit, energy is transferred. The rate at which this charge flows or moves in a circuit is known as electric current. Typically, it is taken as the opposite of the movement of electrons. Okay, so electrons would go in this direction, and we say current moves in the opposite direction. Now, Typically, this is a electrical engineering class, so we do not typically go into the physics of things, because there is a fine line between learning about the physics and learning about electrical engineering. And so during the entire quarter, I might talk a little bit about the physical basis and the physics of things, but we will not go too deep into it. So again, electrons move in one direction, current goes in the opposite direction. Symbol for a current is right here, I. I don't know why. There have been many theories about why I was chosen, but it is what it is, right? The unit for current is amperes, and noted by an uppercase A. Uppercase A. And current always needs a closed path to flow. Okay, it always needs a closed path to flow. If the path is not closed, meaning there is no physical connection between one point and the other point, or between any 2 points, current cannot flow. So current is like a vehicle that you're driving down the street. If the street has, it's broken or it's a dead end, then you cannot drive down that street. So similarly, current cannot flow through an open pathway. It needs a closed pathway to flow through. So in this case, you can see current IA for element A is flowing upwards, right, in that direction. What happens when it reaches this junction at the top node? It splits, right? It splits or it joins up. Basically, if you have two or more currents meeting at a node or at a junction, they're either joining up or they're splitting up. So in this case, we are told that the current for C is moving towards the left. Current through IA, current through A is moving towards the right. And then current through B is moving down. So logically thinking, if you show this to a layperson, if you just say this is a vehicular traffic diagram, what can you see? You have IA coming in, you have IC coming in, and we have IB leaving that junction. What is the relationship between the three? Anyone can answer, yes. Yeah, that's the mathematical quantitative description. But in general terms, IA and IC are combining to form IB. Make sense, right? So qualitatively, we can say, let me write this down as node 1, N1. So at N1, I can say IA and IB are combining, IA and IC are combining to form IB. So mathematically or quantitatively, I can write the expression IA plus IC is IB. And that's it. That is KCL. We look at the current directions. We look at the junction. We look at the current directions. We simply put all the currents entering the junction on the left side of the equation and all the currents leaving the junction on the right side of the equation. And you have our KCL equation. Balances out. Make sense? Right? And similarly, you can apply KCL at any node. It's law of conservation of energy. All the currents entering a junction have to add up or sum up to the currents leaving the junction. So if you apply it at the bottom node, let's call this N2, IE plus IB plus ID. They're all entering the junction. Nothing on the right side, empty, meaning it equals to 0. Theoretically, this is possible. Practically, this has no physical basis in real life. This is Die Hard 4, basically. Anyone remember that scene where all systems go, all lights are green? It's not physically possible. Okay, but theoretically it is. The only thing is that one of these currents, or maybe more than one of these currents, the direction is probably flipped. So we have IE, IB, and ID all entering the junction. Nothing is leaving, right? Yes. No, it is just assumptions on our part. So it's assumptions on our part, or maybe the problem is given to us in such a way that the directions are just meeting up like that. But basically, when you first begin analyzing a circuit, let's say an engineer is designing a circuit, we don't know. We just start making assumptions, right? That's how we actually start circuit analysis. When we have a new circuit in our hands, we have no idea what voltage or what current is appearing in what parts of the circuit. So we make certain assumptions at the beginning of our analysis. When we make those assumptions, we just roll with it. We do not change those assumptions in the middle of our analysis. So let's say we assumed all three directions. It just happens that all three directions converge to the same point. Well, one of those or more than one of those would probably be reverse or opposite. So mathematically, what do we do? If it's opposite of the flow of our assumption, what do we do? No, the equation still remains the same. Equation doesn't change, but you're correct. You're correct in the negative. Anyone else? One of those, or maybe two of those. We don't know. At this point, we don't know, but you're correct. Both of you are correct. Right? You can change the equation as you suggested, but then when we change the equation, we don't change the values or the sign of the values. Or if we change the sign of the values, then we don't change the equation. So either ways, otherwise it gets complicated. So either ways, both are correct. But what we do is we simply take the directions, we write out our equation, and then we plug in the values, or we determine the values, as the case may be. Okay. So either one of these three or two of these three would probably be negative, not positive. All right. Let's take a 10-second pause. Think over that and let me know if you have any questions. Any questions? There it is. Okay, so now if you look at the values, IA is given to us as 6, IC is given as minus. If IC is given as minus, what does it mean with regards to the direction? It's in the opposite direction, right? So we can either use the equation as it is along with its value, which is minus 2 amps, or we can flip the direction and write the equation. If you flip the direction and write the equation, it gets a little bit more complicated. So I advise students not to do that. You simply write out the equations based on the direction of the arrow, and then you simply plug in the values as they're given to you. So in this case, at the top, if I apply KCL at the top, I have what? IA, IC, and I need to find IB. So this would give me 6 plus minus 2 equals IB. Okay, so IB is just 4. Never forget your units. As easy as that. You can flip the sign and make it 2, but then you'd have to change the equation also. So do not do a double flip. I would always advise students, just write out the equation as it's given to you, and then just plug in the values as they are given to you. Chances of errors will be minimized. And then there are, so you can then find ID also. Any questions? Make sense? Yes. Mm-hmm. No, not really. Both are appropriate. So the question being asked is, should we use uppercase I or should we use lowercase I? So as the case may be, they're interchangeable. Sometime later in AC analysis, we'll use an uppercase I. We'll also have a lowercase I, but most of the time you'd see lowercase I. There are some practice problems here. I'll go quickly over those practice problems. IA, you have two currents coming in. IA is simply 1 plus 3. Here, IB is coming in, 1 amp is coming in, 3 amps is coming in. So I have IB plus 3 plus 1 equals 2. And then, let's see, all 4 currents coming in. So I have IC plus 4 plus 1 plus 3 equals 0. Right? All the currents coming into a junction are on the left side of the equation. All the currents leaving the junction are on the right side of the equation. Yes. So if I understand your question correctly, is actually it doesn't matter. So if you are stating that you assumed a current direction at the beginning of your analysis and your answer turns out to be negative, you can leave it as that. You can leave it at that, okay? Because I would know that you've chosen a direction and then your answer matches up along with the chosen direction. So the question being asked was, what do we do in case our final answer turns out to be negative? Should we flip the arrow that we assumed at the beginning of the problem? The answer is you can leave it at that. Okay, if you assume a specific direction at the beginning of your analysis and your end answer or final answer turns out to be negative, I will know. As long as the magnitude is correct, as long as your magnitude is correct, your answer is also correct, depending on the current direction that you chose. Okay. All right, any questions before we move on? Yeah. Sure. Absolutely. Good question. So IA and IE, and let's call this node 3, are both leaving the node. Okay, in the previous problem, IA and IE, if you apply KCL at that node, you can see both of them are leaving the node. So you would write 0 equals IA plus IE, meaning one of them is negative. You can write IA is minus IE or IE is minus IA. You have to understand the minus sign is for us humans, okay? So that we can balance out our equations. If you don't put a plus or a minus sign in front of these quantities, our equations would never balance out. Okay, current, voltage, power, energy, they are never positive or negative. They just have a value. Your power supply, your power adapter, your chargers, you would say it's a 100-watt charger. You would not say it's a minus 100-watt charger, right? So power is never negative. But in order for us to balance out the equations, we put a negative in front of those quantities. Okay. Voltage law. Voltage law was with regards to voltages around a loop. Voltage is nothing but the transfer of, anyone? Voltage is the transfer of energy per unit of charge. Okay, that's another homework question. That's your answer. Okay. Similar to node, we have a concept of a loop. Loop is basically any closed electrical pathway in a circuit. Basically, if you start at one point in a circuit, you go around the circuit and you're able to come back to that same point, it forms an electrical loop. You start at any other point and you come back to that same point. That is another loop. And loops can be multi-level. So you see loop 1, you see loop 2, and you also see loop 3, which is basically the outer loop. Okay, so you can have loops inside of a loop or nested inside another loop. So here you have 3 loops, loop 1, loop 2, and loop 3. All of them form a closed pathway for current to flow through. And it doesn't matter what loop you take, when you sum up the voltages or the voltage drops around that loop, they will always, always, always sum up to 0. Okay, they will always sum up to 0. Law of conservation of energy. I've been studying EE since 1992, when I first started as a student, and it's still, this is just beautiful to me. KVL, it just always adds up. Doesn't matter how big a circuit is, how big a loop is, always adds up to being 0. All right. So we have element A, B, and C in loop 1. Voltages are basically caused when electrons or current flows through an element, and it causes a drop in the potential level across that component. Okay. Electric voltage is nothing but the difference in electric potential between any 2 points. Okay. So loop is a closed pathway. Voltage is the transfer of energy per unit of charge, but it is the difference in electric potential between any 2 points. Those 2 points can be far apart or can be close together just on either side of a component. Okay. And with relates to a base level of ground, which is literally our electric supply actually goes into the ground. So we say ground or earth, which has 0 potential, 0 volts potential. You can measure the voltage between any 2 points, and the difference in the potential is defined as that electrical voltage. So if you have 2 points, let's say the surface of this table was 0 volts, ground. And my right hand here is at 5. Okay. Level of 5. So the difference measured with respect to ground to this point level here is 5. If I raise my left hand and put it at the same point, the difference between ground and my left hand is also 5. But if I measure the difference in electric potential between these 2 points, what voltage value would you expect? 0, right? So voltage is the difference in electric potential between any 2 points. It requires a reference point for measurement. Okay, if a reference point is not specified, then it's typically the ground or the negative end of the power supply in that circuit. Okay, so again, it's measured between 0 and any level you want, but it's always between 2 points. If 2 points are at 100 volts, the difference between those 2 points is 0 volts. Doesn't really matter what value it has with respect to ground. Okay, but it always needs a reference point of measurement. Okay, so if you have a component like this in a circuit, which is component A, and you're measuring the voltage across it, we specify which point is higher than the other. Okay, which point is higher than the other, and that is noted by the plus and the minus sign. So plus and minus indicates which point or which end of that component is higher than the other. And that is defined as the polarity of that voltage. Okay, polarity of the voltage. In this case, it simply states that the top end is higher than the bottom end. And hence a plus and a minus. So plus and a minus simply notes the polarity of the voltage, simply tells us which end of that component is higher than the other point. This plus and this minus is only for that element A. It's not with reference to anything else. Okay, it's not with reference to anything else. So you have a plus and a minus here. And then students sometimes do get confused. How can we have a minus, minus, and a plus all at the same node? And that's exactly the point. The plus and a minus sign that you see across every component is only with respect to those two terminals of that component. Okay, it does not affect, it does not notify anything about the rest of the circuit. Okay, so when you apply KVL, when you sum up the voltages, you have to take these polarities into account. Now, when you sum up these voltages, let's pick a loop. Let's say I want to add up the voltages in loop 1. Okay, if I want to add up the voltages in loop 1, what I'm going to do is I'm going to go around the loop. I pick a starting point. I typically pick the bottom left corner of a loop. And I just note down all the voltages that are present in that loop. So in this case, I have VA, I have VB, and I have VC. And I know that they should all add up to 0. Okay, VA, VB, and VC should add up to 0. Now the question is whether I should put a plus or a minus sign in front of these voltages. Okay, so what I do is I go around the loop in a clockwise manner. And the sign for the voltage that I encounter first is what I put in front of the notation in the equation. So if I start going in a clockwise manner, the first sign for VA is minus, negative. So I put a minus sign in front of VA. Next is VB. I have a plus. So it's plus VB. And the next is C, which is plus. So I put plus VC. And then I have my KVL equation is equal to 0. If you have a preferred method of applying KVL, you can stick with it. You don't have to use what I am showing here. Okay. You have been studying KVL and KCL for longer than what we are going to study here. So if you have a preferred method that you're comfortable with, you simply keep applying those methods. Okay, you do not have to use this method. All right. But does this method make sense? Right. I simply pick a direction, whether you pick clockwise or counterclockwise, doesn't matter how you sum up the voltages, whether you add minus plus or plus minus, you will end up with the exact same equation, no difference. You can practice this multiple ways. If you need extra practice, again, the homework has some tutorials that you can do. Those are all for extra credit. And once you go through those, if you have any questions, you reach out to me. And KCL homework is due tonight. KVL is due tomorrow. And then there's power and energy or circuits and voltages that's due on Wednesday. So let's, I think we have a few more minutes. Let's look at the outer loop. Okay. So in the outermost loop, loop 3, this is loop 1. Loop, not loop 2. Let's do loop 3. I can see I have 1, 2, 3, 4 voltages. So I'm going to write down VA, VB, VD, and VE equal to 0. I start at the bottom left corner and I go around clockwise. Minus VA plus VB minus VD plus VE equals to 0. If you go in the counterclockwise direction, you would get the exact same equation, right? You get minus VE plus VD minus VB and plus VA equals to 0. Signs would be flipped, but the equation mathematically is still the same, no difference. All right, any questions? So there's an online discussion forum. The purpose of that forum is, since we are all here from very different fields, very diverse background across all fields of engineering, you may or may not know each other. The reason and the purpose for asking you about the calculators is because you will use these calculator devices to perform complex math. Like literally, when I say complex math, I'm talking about complex numbers. Okay. Polar coordinates, rectangular coordinates. There is a worksheet on the website, on the slides page, the page where I have the slides. It talks about polar to rectangular conversion and rectangular to polar conversion and performing mathematical operations using complex numbers. Each and every student needs to be proficient in performing these calculations on your own devices. Since everybody uses multiple, different devices, but thankfully there are similarities between all of them. If you do not know how to do this, you look it up on the internet, on the website, or you reach out to your peers, and then, well, learn how to do those, right? There's a practice sheet on there. You won't need it until probably like 6 or 7 weeks into the class, actually like 6 weeks into the class, but you would take a look at it right now, okay? Because it will require a lot of practice going forward. So you need to know how to do this, not just for this class. As engineers in your own field, you will encounter areas where you need to do complex math, okay? So go ahead and open it up, take a look at it. Plan to spend at least a few hours every day on each class. So I know this class is not a priority to many students. I've done this class for many, many years. But again, I would say spend at least 1 or 2 hours every day. Just set aside 1 hour at least. If you get bored after an hour, move on, that's fine. But set aside at least 1 hour every day to take a look at the class material and the homework assignments. All right, I'll bid you a good day and I'll see you all on Friday.
Thank you.
Mhm.